Hey, welcome back. Last few videos we talked about deriving the kinematic equations for constant acceleration using geometric and algebraic methods. Today we'll derive those same equations, but we will do it using calculus. Um, Keep in mind, calculus was invented in order to make the algebra or the physics easier. There's things you can do with calculus that just it's not elegantly done in algebra. So calculus, I guess you can say, makes physics easy. So this is primarily for all the calc students. If you do not know calculus, view some other videos out throughout the internet and then come back and approach this video once again. But the kinematic equations we've been talking about so far are for constant acceleration. And we've used that. We've drawn graphs, acceleration versus time, and hey, if it's constant, it's a line, right? And if this is some point t, we've talked about the area inside of this being your change in velocity. Well, alright, that's great. For all the calc students, you should know that the area under this curve is the integral of A. So, what is A? We've talked before about, especially if you're thinking about it in average terms, like average acceleration is equal to the change in velocity over the change in time, versus instant acceleration is equal to the change in velocity over the change in time. Except these changes are infinitesimal. They're really small. So, first we'll begin by writing this equality. So we have, let me change colors, we have dv dt is equal to A. This dt down here, we're going to move it over to the other side, multiply each side by dt, and from there we'll integrate. So we have dv is equal to A dt. Okay? Now, if we integrate both sides, on this side, the variable we need to respect is velocity. So we're going to look at it from our final to our initial, the actual values being arbitrary. They could be anything. We're looking for a general case description. Over here, our final time is going to be t, and our initial time is going to be 0. We're just looking at it from some point we decide is the starting time, hit our clock, and we end it at t. So that's why the first one's 0. Alright. Now, if this looks confusing to any of the calc students, if I showed you this, you would easily answer x plus c. Now keep in mind we're doing a definite integral, so we'll be evaluating at these 2 points. We won't need this c. But it's the same thing here. It's not any different. So what we have is v, we're going to evaluate that at v final and v initial, and that's going to be equal to at, because a is a constant, so we treat it like a number, and we do the same thing with dt. And you integrate it and you get t, so at. And we're evaluating this at t and 0. Now when you evaluate those, you should remember that you're going to plug in this value, and then you're going to subtract this value. Alright, so let's do that. So you get vf minus vi is equal to at minus 0. But I won't go ahead and write that here. Solving for vf, we get the final velocity is equal to the initial velocity plus acceleration times time. And this is the first one. So if that was at all confusing just for the first equation, you really need to review your calculus. And in essence, this is almost identical to what we were doing in the geometric video. We are finding areas under the curve. Well, that's still what we're doing here. Nothing has changed in that department. Alright, so let's begin working with the the next equation here. And if you look at this equation, just from algebra, what kind of polynomial is this? It's a line, right? And in the geometry video, talking about where these equations came from, we showed it to be like this, where this is velocity and this is time. And then we talked about, now this would be the initial velocity here, this is where you start, right? We talked about how the sum of these areas under this curve is displacement. Alright? Now, if you know what this line is, and you know calculus, then from here, you should be able to derive the equations for position without having to use the geometry method. Alright? So, let's think about VF here. VF. What is VF? Well, in terms of average velocity, we have change in position over change in time. But for instantaneous, we have change in position, over change in time. These are identical, except this one's taken over 2 points that could be far away, or they could be close. So this change in t could be super small and pretty much be dx dt. But this one is where these little changes in increments are so small that we can call it instant. And you should know this. Now, for VF here, we're going to substitute dx dt and follow the same pattern that we did in the last slide. So, VF is dx dt, so we'll write that, dx dt, and that is equal to the initial plus at. Now, we're going to do the same thing we did for the last one. We want to integrate this side with time, so we're going to move the dt over, multiply both sides by dt. Okay? See, if you multiply dt here and dt over here, these ones cancel, and you now have something you can integrate. Alright? So, let's continue it. We have, from here, dx is equal to vi plus at dt. Alright? Now what do we do from here? We integrate. Now here, we're going to start at some spot and we're going to end at some spot, right? As far as position goes, there will be an initial position and there will be a final position. So here we'll write initial and position final. Over here, we're using our stopwatch. We start at 0 and we're going to end at some time. Alright? Integrating, this one should be easy. It's just x, and we're going to evaluate that at x final and x initial. And that's going to be equal to, now, when you integrate this, remember the rule of the integrals. You can actually integrate this and integrate this separately, since they're the sum of two integrals. Alright? So this one here, when you're integrating with respect to time, this one here becomes initial velocity times time, and this one here becomes 1/2 at squared. Now you may be wondering why, if you're not that strong at calculus. Well, if you were to take the derivative of 1/2 at squared, which is really easy to do, this 2 comes down, cancels out this 1/2, and you're left with at, because the rule is you subtract 1 from the exponent. Alright? So if you go back up, you need to add that 1/2, and so it's half of what if the exponent's going to become 2, you need to multiply by its reciprocal, 1/2. And if any of this is challenging, You definitely need to review your calculus because physics is easy when you know calculus. Okay, so, and we're evaluating this one at t and 0. So this one, plug in xf, we get xf. We subtract xi, and that's going to be equal to, now we know the second part of this is going to be 0, so I won't bother writing it. And when I plug t in for t, I'm just going to get the same thing I already have inside the parentheses or brackets. So you're left with VIT plus 1/2 AT squared. Move the initial over. I'll try to write it over here in this little space I have as nicely as I can. We're just moving the initial position over, and we get the final position is equal to the initial position plus the initial velocity times time plus 1/2 AT squared. So there's your other kinematic equation. Now a lot of students often wonder, why can I only use this when acceleration is constant? It seems like I should be able to use it anywhere. This is why the geometric video and this video show the only reason you can use these equations for constant acceleration and only acceleration is because they are derived from constant acceleration. Remember, we started with the original graph. Remember, it was constant. We would not have gotten this from integrating if this was not constant. Has to be. Alright, physics deals, and science in general, deals with how things change over time. Calculus itself was designed to make physics easier. If anyone's ever told you calc-based physics is harder than algebra-based physics, they lied to you. In order to solve problems through algebraic methods, at times it can get quite cumbersome and complicating. You're going to be using, it's just going to get ridiculous. Whereas with calculus, it's very elegant, very simple, and happens really smoothly. So remember that. Calculus makes physics easier. You need to start approaching physics through the calculus mindset. For instance, I want to show you really quickly how quick these formulas can be devised. Well, I know, one sec, I know A is equal to dv dt. So that's where I'm going to start. Here we go. dv dt is equal to A. dv is equal to A dt. Integrate at Vf to Vi and integrate t to 0. That gives me Vf minus Vi is equal to, is equal to At. So Vf is equal to Vi plus At. First one. I know that V is equal to dV, d change in position over change in time. So let's do it again. I'll substitute that value in here for Vf. I get dx dt is equal to Vi plus At. So move the dt over. I get dx is equal to Vi plus At dt. Okay, integrate at x final, x initial, and here I'm going to integrate at 0 and t. This here is going to become x. I'm going to evaluate it at x final and x initial. So what I'm going to get for this one is x final minus x initial is equal to, now here it's the sum of two integrals. So here I'm going to get VIT and then 1/2 AT squared. I'm not going to subtract anything from it because it's 0 here. So VIT plus 1/2 AT squared. VIT plus 1/2 AT squared. Move the initial position over if you really like to. I don't really mind myself. I prefer to keep it on the left hand side, but we'll do it. So VIT plus 1/2 AT squared. Not hard. Keep in mind, what if acceleration wasn't constant? What if they told you it was linear and then they asked you for the function of position with time? Well, you're going to have quite a difficult time trying to figure that out. If you're trying to use algebra, and even geometry could get extremely complicating. With this, easy as pie, you just integrate. Thanks for watching.